This is a brief overview of fluid statics. Two important quantities in fluid statics are pressure, capital P, which is equal to force over area, and uh, density, rho, which is equal to mass over volume. We'll be dealing with incompressible fluids, which means that the density throughout a fluid remains constant. And if a fluid is incompressible, it also means that it follows Pascal's principle, which means that pressure applied to a fluid um, is transmitted throughout the entire fluid without being diminished. So one of the most important concepts in fluid statics is hydrostatic pressure, and that is the pressure a fluid gains based on how like deep it is. So let's say we have some container here with a fluid inside. We want to know what the pressure is at a certain depth. And so we can consider a column of water here. So let's just take like this small column of water. Now, since it's static, it means that this column of water is not moving. And so the net force on this column of water is zero. Now, if we draw a force diagram for this, we have the weight of this column of water. And then we also have another force here that's being applied from the pressure, the net pressure on this column of water. Now, pressure acts on all surfaces. So we have pressure, I'll put it in green. Pressure from this fluid is causing a force on all places where there's area on the surface. So all around. But the pressure on the sides of this column of water cancel out because there's pressure going one way and there's also the same pressure from the opposite direction. So we only need to consider the pressure from the top and the bottom. Now we'll call this top pressure P0 and the bottom pressure P. So since we know that pressure is equal to force times area, the force that pressure over an area causes is just so force is equal to pressure times area. Now we want this force to be equal in magnitude to the gravitational force. So we want this net force here, which is the difference between the force caused by the pressure at the bottom and the top to be equal to gravitational or the weight of this column of water. So the column of water has force from gravity equal to mg, and then we want this to be equal to the net force from the pressure. So this is equal to P minus P0, since it's an upward force, times area here. Now we can denote mass, we can write mass as we see here, mass is equal to density times volume. So we have rho Vg is equal to pressure minus the initial pressure times area. And then we can write volume here as just the area of this, the top or bottom surface of this column of water times the height of the column of water. So this here is the height. So now we can write rho, so the density of this column of water times, or any fluid, times the area of the top or bottom surface times the height of the column times gravity is equal to the pressure at the bottom minus the pressure at the top times the area. You see that area here cancels out. And then doing a bit of algebra, we can rearrange this equation to get the pressure or hydrostatic pressure at the bottom is equal to the initial pressure plus rho GH. So this makes sense because we have hydrostatic pressure is equal to initial pressure plus the additional pressure that's caused by the mass of the fluid. So this is a really important formula to know, and that is hydrostatic pressure of a fluid at a certain depth. And so this, as you can see, only depends on density, gravity, and the depth of the fluid plus the initial pressure. So it does not depend on like the location, which means that the pressure given the same density throughout the fluid and same uniform gravitational field will be the same as long as the height is the same. So if we have a contraption that looks like, you know, a U-shaped tube here, or here, so we have like a U-shaped tube, and then we have some fluid here that's the same density and at the same height. At the same height, the pressure is going to be the same. So like pressure 1, pressure 2 here, they're all the same as long as the height is the same and the density is the same, which means that even for contraptions that look like, I don't know, something wonky like that, as long as I said the fluid density is the same, then the pressure is going to be the same at the same height. So if you like consider the pressure at the bottom here, this is going to be equal to the pressure here and the pressure here because they're all at the bottom of this, and the height underneath the surface is the same. So it doesn't matter how like wide or how big of an area the container is, as long as the height underneath the surface is the same and the density and gravitational field remain uniform, then the pressure is the same. So when we have a tricky question is if the pressure is the same, let's consider 3 containers. So one shaped like that, one shaped like that, and we have the last container shaped like this. Now all these containers have the same width, so let's just call it like 1. So the width of all these containers is the same, and then the height of water on all these containers is also the same. So this has water filled to the same height. Now the pressure at the bottoms of all these containers are going to be equal. However, if we put this on a scale, we know that the weight of this, let's call this A, B, and C. Weight of container A, or with the fluid, is going to be less than the weight of container B, which is going to be less than the weight of container C. However, the pressure here, pressure of container A at the bottom is equal to the pressure at container B and the pressure of container C. So this is pressure at the bottom. Now, if the pressure at the bottom is the same and this area is the same, then you might think, how can the weights be different? And this is seemingly contradictory. However, like I said before, pressure acts on all areas. So here we have pressure acting downwards, which causes the weight, and then pressure acting at the sides here, which cancel out and don't contribute anything. Now for this one, we have pressure acting downwards, which contributes to the weight. Then we also have pressure acting at this angle. And now a component of this pressure is going to be acting sideways, and these get canceled out. But then another component, so a component of these acts sideways and get canceled out, but then another component of this angled pressure acts upwards and then cancels out with some of the pressure that acts downward at the bottom, which causes the overall weight of this container with fluid to be less than um, this 90-degree container. And then for container C, we have pressure acting downwards at the bottom, but then we also have pressure acting at this angle here. And again, a component of these acts sideways and gets canceled out, but then a component of them acts downwards and contributes to the weight of this container, which causes the weight overall to be greater than the weight of the 90-degree container. And so another tricky problem here could be considering, again, a U-shaped tube, but then with two different fluids. So let's just say we have water here. So this blue fluid is water, and then we have another fluid, such as oil, that is less dense than water. So oil takes up this volume, and then water fills up the rest of this too. And then we might ask, okay, well, what is the pressure at this level? So what is the pressure here? The pressure at this point here is going to be the same as the pressure at this point, because we only consider the water as the fluid here. So since the water isn't moving and this is at the same level, and the density doesn't change because this doesn't go, it's at the surface between the water and the oil. So we can't really say that like the density here changes because it's at the boundary. And then like if we ignore this oil and water here and pretend like we don't know what this is, we can't tell that it's oil or water. We just know that there's a pressure going downwards on this surface and a pressure going downwards at this surface. And since these are at the same level and there's water underneath it, they have the same pressure. However, if we consider the pressure at another point, like let's say here, this pressure, we call this P1 and P2. P1 and P2 are not equal because while they're at the same level, the density of oil is less than the density of water. So rho 1 is less than the density of water. So the pressures are not going to be equal here. Okay. And then from this, you should actually be able to tell that the pressure at point 1 here is greater than the pressure at point 2 because the pressure at the bottom is at the same and the pressure at the top is just atmospheric pressure. But then this is around halfway down the oil. So it will be halfway between this pressure at the bottom and atmospheric pressure. Well, this, let's just say it's like a third of the way below. So this is only a third of the way from atmospheric pressure to this bottom pressure. And then we can see that because if we draw another line here, like right here at the top, this here is going to be atmospheric pressure, but then this here is going to be atmospheric pressure plus some pressure from the oil that's above it still. So when we have a less dense fluid sitting on top of a more dense fluid, and you compare it at the same height, generally the less dense fluid is going to actually have greater pressure at that height than the more dense fluid. But then anything underneath this line where it divides it, we see the fluid is just the same. So the pressure is going to be the same given that the height is the same as long as the fluid remains constant and the density remains constant. So since this section has constant density, then the pressure is going to be the same at the same heights. Now we can also apply this to hydraulic lifts to see why we can lift heavy things with a light car, or like with a light force. So we can lift a car with a light force because of the differences in area and then the pressure being the same. So let's consider a lift here. So we have a large output area and a small input area. And I'll call these the same height. So this is filled with a fluid. Now the pressure here, pressure at point 1 is equal to the pressure at point 2. So these are equal. But then the area here, area 1 and then area 2. Area 1 is greater or less than area 2. And we know that since force is equal to pressure times area, since the pressure is the same and area is area 1 is less than area 2, we know that force 1 is less than force 2, even though this is static, so this isn't moving, but the force required to keep this static at the input is going to be less than the force required at the output. So this is why putting a small force at the input here can lead to a dramatically higher force at the output. And then this force, the difference is force out over force in is equal to area out over area in, as we can see here. So a larger output area with regard to the input area leads to a larger output force over input force. Now, since the fluid is incompressible, we know that the volume also needs to be conserved. So a change in volume in the input has to correspond to the same change in volume in the output, which means that the distance that this input piston for like a hydraulic system pushed down times the area of the input, which is the volume. Basically, this is the volume of the input. The change in volume of the input has to be equal to the distance that the output moves times the area of the output, which is equal to the volume change of the output. And from this, we can see that since force is directly proportional to area, we have that force here. So distance times force 1 times pressure is equal to distance times, or force divided by pressure here. It should be, so area is equal to force divided by pressure. Distance 1 times force 1 divided by pressure is equal to distance times force 2 divided by pressure. And then we can cancel out the pressures, and then we get that force 1. So force 1 times distance 1 is equal to force 2 times distance 2. And this is equivalent to saying that work 1 is equal to work 2, which means that no energy is gained or lost in the system, which shows conservation of energy. Okay. Finally, another common type, another important concept based on pressure is buoyancy. And so we know that when we put something in water, the water has the pressure from the water causes a buoyant force that acts upward on the object. So again, let's consider this container here, and then we have some object inside, right? And then we're holding it by a string or a rod here so that it stays in place. And then it's being surrounded, it has water surrounding it. We want to find the buoyant force on this object. And so we know that the pressure at the bottom here is going to be equal to, let's call this H, and then we'll call the top of this A. So this is the area of the surface, top or bottom surface, and then H is the height of the object. So we know that gravitational force, or if we're only considering buoyant force, we know that the pressure at the top is going to be some value. Let's just say this is P0. The pressure at the top is P0. That means the pressure at the bottom here is going to be equal to P0 plus rho GH, because the pressure at the bottom here from the water or the liquid only depends on the height of the liquid, since the uniform because of its uniform density. And then we know that force is equal to pressure times area. So we have the net buoyant force on this object is equal to, since these cancel out, we have the net buoyant force on the object is equal to P rho GH times the area. And then this we can just simplify to volume. So the buoyant force on an object is equal to rho VG, where this rho here is the density of the fluid. So this is important to remember because it's not the density of the cube here. We don't need to know the density of this object. We just need to know the density of the fluid, because the fluid is what creates the hydrostatic pressure that creates the buoyant force on the object. So the buoyant force on this object is equal to density of the fluid times the volume times gravitational force. And so this volume is the volume that this object displaces. So the buoyant force is going to be proportional to the volume of water that it displaces. It doesn't depend on the density or the mass or even the shape of the object itself. It only depends on the volume of water that the object displaces. And so one common type of question to ask for this is, let's consider we have an iceberg floating in water here. Now you know that icebergs are mostly underwater, but they stick out on top and then they float, which means that the buoyant force has to be equal to the gravity or the weight of the iceberg, since it's floating. It's not sinking downwards. Now we want to know, what is the proportion of the iceberg that's underwater? Well, we know that the buoyant force is equal to the weight of the iceberg. So if we draw a force diagram here, we have the weight of the iceberg is equal to the buoyant force on the iceberg. Now, we know that the buoyant force here is equal to rho VG, and remember this is for the displaced water. So V here refers to this volume. So this is V, not the volume of the iceberg. And then we have here the gravitational force is equal to, go back to white. Gravitational force is equal to mg, which is also equal to rho vg, but this v refers to, I'll call this vw. So vw is the volume of water that's displaced. And rho vg here, this v refers to the volume of the iceberg. So the density of the iceberg times the volume of the iceberg gives the mass of the iceberg. This is the density of the water. Density of water times volume of the water gives the mass of the water here. So we know that these two are equal. And since it's floating, we know that the density from intuition, or from what we have observed before, we should know that things less dense than water float. And this will tell us why. So we know that the density of the iceberg is less than the density of water. Okay, so since these are equal, we can set these equal to each other. So we have here density of water times volume of water displaced times gravitational field strength is equal to density of the iceberg times the volume of the iceberg times gravitational field strength. And now you see that the g's cancel, and then doing algebra, we can rearrange this to be the volume of the water displaced, which is the proportion of the iceberg that's underwater, or the portion of the iceberg that's underwater divided by the volume of the iceberg. So this is the proportion of the iceberg that's underwater, is equal to the density of the iceberg over the density of the water. So now this generalizes to a lot of different scenarios. It doesn't have to be water and it doesn't have to be an iceberg. But as long as the density of an object is less than the density of the fluid that you put the object in, part of its volume, only part of its volume is needed to provide the buoyant force to lift the object, which means that part of the object will not be inside of the water or the fluid that it's placed in. So if you had something that was half as dense as the fluid is placed in, then only half of the object would be submerged. So the three important equations, or the most important equations that you need to know for fluids, in static situations, is the static pressure for fluids. So the pressure is equal to the initial pressure plus rho gh, and the buoyant force exerted on an object by a fluid, which is equal to rho vg, where rho is the density of fluid and v is the volume of the displaced fluid.